In this video, we're going to look at two more examples of addition reactions to alkenes, halogenation and halohydrin formation. So halogenation is simply adding two halogen atoms to our double bond, and the reagent is just the halogen molecule. It turns out halogenation is only practical with chlorine and bromine. Halogenation with I2 is poor, giving low yields, and halogenation with fluorine is simply too violent. The halogenation reaction is stereospecific, and the halogen atoms add with anti-addition. So we've previously seen examples of syn addition, where both groups add to the same side. In anti-addition, the two halogen atoms are going to add to opposite sides of the double bond. So one will go up on the wedge, and the other will go down on the dash. And we have to be aware that we will very often get both enantiomers in this halogenation reaction. So let's take a look at the mechanism. We're going to talk about bromine, but the same thing would apply to chlorine. So both bromine and chlorine are nonpolar, but they are polarizable. And so the approach of a nucleophile will induce a dipole moment, a nucleophile like the extra pi electrons in our alkenes. And so we can think of bromine as a bromine atom bonded to a good leaving group, because when we induce that dipole moment, right, the negative end will become our leaving group. So we might think that this proceeds with a carbocation intermediate like our hydrohalogenation and our hydration, but it turns out the formation of a carbocation is not consistent with the stereochemistry. It's not consistent with the anti-addition that we observe. So this is not the correct mechanism. So on the next slide, let's look at what actually is the correct mechanism. So it turns out the actual mechanism is consistent with formation of what's called the bromonium ion. And this is where we have this bridge structure that's very similar to the intermediates that we have in the oxymercuration demercuration. And so because we form this bromonium ion, which sort of blocks both top sites in this example, the other bromine that comes in to act as the nucleophile must come in from the opposite side. And so this results in the bromine atoms adding to opposite sides of the double bond. Okay, and halogenation is said to be stereospecific. So the stereochemistry of the starting alkene determines the stereochemistry of the products. For example, cis-2-butene and trans-2-butene give us two different products. In the cis example, we get a product and its enantiomer. In the case of trans-2-butene, we actually get a meso compound, right? This is what we would predict for the addition of the bromine, right? But we can rotate around this single bond, and when we write the molecule this way, right, we have a plane of symmetry. So this molecule is meso, and it is not chiral. It does not have an enantiomer. So halohydrins are formed when we add a bromine and then an OH in place of a second bromine. Now I know I've written a water here, but just like in the hydrogenation, we can have another base, most like another water molecule, come and deprotonate this ion. And formation of halohydrins proceeds by a very similar mechanism as the hydrogenation. It just happens when we do the halogenation reaction in water. Rather than adding a second halogen, we add one of the solvent molecules. The reason being, if the water is our solvent, then there are a lot more water molecules than there are bromide ions. So just through sort of statistics and probability, we're more likely to add a water than we are to add another halogen when the reaction is conducted in water. So if we think about the mechanism for halohydrin formation, it starts off just like the hydrogenation. So the pi bond attacks the halogen molecule, giving rise to this bromonium ion. But now rather than having another bromide ion act as the nucleophile, we're going to have a water molecule do the nucleophilic attack. And then to finish it off, right, we'll have a base. In this case, because we're doing this reaction in water, the most likely base is going to be water. It will come in and take the proton from our ion, giving us the neutral product. So halohydrin formation, right, we're adding a bromine and an OH, just like hydrogenation, they're going to add in an anti-fashion. Okay, now in the halogenation, we don't have to worry about the regiochemistry because we're adding two of the same atom. In the case of halohydrin formation, right, we're adding a Br and an OH. So where does the Br go? Where does the OH go? So it turns out the halogen, or the halide, is going to add to the less substituted carbon, and the OH will add to the more substituted carbon. All right, so I think we can rationalize this regioselectivity by looking more closely at the mechanism. So we start out with our pi bond attacking the bromine, and then formation of this bromonium ion. Then the water acts as the nucleophile. It attacks the more substituted carbon from the alkene, and then we get the deprotonation. So why does it attack the more substituted carbon? Well, if we think about what that transition state would look like, we sort of have the picture down here. And so the positive charge has to be transferred from the bromine down to the oxygen. And so it's sort of got to go through that carbon atom, right? And so in the transition state, we sort of have an approximation of a carbocation. And so we know that a more substituted carbocation is going to be more stable. So the transition state is more stable or lower in energy when the water attacks the more substituted carbon than if it had attacked the less substituted carbon. And so that's why the OH always goes on the more substituted carbon, and the halogen will end up on the less substituted carbon. Okay, so let's look at a couple examples. So we want to predict the major products of the following reaction. And so they just tell us that we're reacting it with chlorine. They don't say anything about the solvent being water, and so we can assume that this is going to proceed by halogenation. And so we're going to add a chlorine to each of the carbons that have the double bond, but we have to add them in an anti-fashion. So we will get one product where the chlorine adds to the top, and so the methyl group will be pushed to the back. Then in the other case, the methyl group has to add, the chlorine has to add from the bottom. That will push the methyl group to the top. All right, and now we need to consider, are we going to get an enantiomer? So we wouldn't if the product that we made was meso, right? But I don't think we have a plane of symmetry here because one chlorine is up and one chlorine is down. And so we will get the enantiomer. So we'll also get the product in equal amounts, where in this case the chlorine is up and the methyl is down, and in this case the methyl is up and the chlorine is down. Okay, here's another example. In this case it's also halogenation. They don't tell us anything about water being the solvent, and so we're going to add a bromine to each one of the carbon atoms on the double bond. And we have a choice on, right, whether we put the methyls on the wedge in the dash or the ethyls on the wedge in the dash. What I usually do is go with the lower priority group, and I sort of put that one on the wedge or the dash along with the bromine. It doesn't really matter how we do it. I just do it that way to be more consistent. And then if I'm asked about determining the R and S configurations, I think that makes it a little bit easier because when I switch them, it's easier to do the switch and see which configuration I have. So I'll put one bromine here on the wedge. That means the methyl gets pushed back to the dash. And in this case, the bromine is going to have to come on the dash. So the methyl will go on the wedge. The bromine will go on the dash. Now again, we need to consider, is this compound meso, meaning it's not chiral and we won't have an enantiomer, or is it chiral, and in which case we'll also get the enantiomer? So it's kind of hard to tell when I've drawn it like this, the way the product was drawn. But remember, we can rotate around these single bonds, and so I could have drawn the molecule, right? If I rotate it so that this ethyl group comes up to the top, right, then that's going to result in the bromine being on a wedge now, the methyl group on the dash, and you can see, right, when I've rotated about that single bond in this way, we do have a plane of symmetry here. So this compound is meso. So, right, I don't want you to think that these are two enantiomers, right? This is the same compound. I just rotated around this single bond, and so we only get one product in this case, because this compound is meso. Okay, one final example. Now in this case, we know we're going to form a halohydrin because now they're telling us, right, that we're doing this in the presence of water. So in this case, water is our solvent. So we're going to add one bromine and one OH. And the bromine should go on the less substituted carbon, and the OH should go on the more substituted carbon. But we do want to do this in an anti-fashion. So, and again, right, I'll choose to, right, the things that I'm going to put on the wedge and dashes from the original substrate, right, the lower priority groups are the hydrogen and the methyl, and so I'll leave the ethyl and isopropyl on the straight lines, right, and I'll have the hydrogen and the methyl that I'll push on the wedges and the dashes with the bromines. So, left the position of the ethyl and the isopropyls alone. So if we put the bromine on the wedge, then that means the hydrogen is going to go on the dash here, but we don't usually draw hydrogen, so I'll leave that hydrogen out. That means the OH has to go on the dash, and then I'll push this methyl to the wedge. Now, this compound is not meso, and both carbons are chiral, so I will get the enantiomer. So we'll also get the product where the OH is on the wedge. That pushes the methyl to the dash. And so then the bromine will be on the dash.